Okay, so the sheet that you have in front of you does not cover all of ionic naming. Um, the sheet that you have in front of you only covers the simplest type of ionic naming. And so once again, we're going to talk about criteria for compounds being ionic versus molecular. And so for our very first beginners ones, we're going to do binary compounds that are ionic. And how you know they're ionic is that they contain metals, and the rules are going to be different. However, I'm going to point out to you that this part of this might come more easily to you, except there's a lot more. So I'm going to bring us back to that folder that was in the notes folder. So when you clicked on the notes, you saw that there were 6 slideshows, and you're still finishing the slideshows because I'm going to remind you again, notes are now not due until Monday, November 25th. So you got a little bit more time, but you do have a quiz on all of this, all of naming, by the time that you come in on Monday. So, one of the things I'm going to go back to here are these naming study guides. And I'm going to show you one more time this handwritten one because I think it's got a good walkthrough of the different types of ionic compounds. So, you're going to notice as you go through this, right? Molecular compounds are to your left. That's what we did yesterday. So when you get down here, you can see that there's pretty much like these are the steps for naming molecular compounds. If you're going to go from a formula to a name, if you're going to go from a name to a formula, and that's it, you're done. There's like, those are the steps. That's it right there. For ionic compounds, things get way more complicated. And so there's a lot more detail, and I tend to break this up into pieces. So to make it easier, it may not make it easier, but um, I tend to first start with binary ionic compounds that contain simple metals. Then we go to binary ionic compounds that contain metals that have what are known as multiple oxidation states. They have more than one charge, and those rules are a little bit more detailed. Okay. And then we have to get into ones that have polyatomic ions, which is actually simpler, not more difficult. It just sort of adds another layer of stuff that you have to know. So you've got um, kind of almost 4 different situations here with ionic compounds. So let's just back up for 1 second. These are the rules for naming molecular compounds. Just this right here. Then, if you want to learn the rules for naming ionic compounds, keep reading because it's the entire rest of the outline. Okay, which makes it seem complicated. It's not that it's complicated, it's that there's a lot of interesting little rules and different scenarios that come up. And that in all your study guides, I do one of 2 different things. I either expand the whole topic out in a lot of detail so I can help to explain it to you, or I summarize it down, try and make it short as possible. You guys have this thing where you think that because something is longer, it's going to be harder for you to do. That's not necessarily the case. I'm just trying to break things down into a lot of pieces for you so that you can see all the moving parts and understand what's going on. That doesn't necessarily mean that this is harder, okay? But it is going to be fundamentally different from molecular naming. So, the baseline for why these different types of names and formulas happen is because these are not bonded the same way. And so, how the atoms are actually holding on to each other is different. Because of that, it changes the dynamic of what you can and can't do with them. So I suppose this is like saying in the world, right? You could build things with Legos and make stuff out of Legos, or you could build stuff with Play-Doh and you can make stuff out of Play-Doh. Both things make something, but they don't make something in the same way, right? Legos are probably simpler than Play-Doh. Because in order to make Play-Doh into lots of different things, you need a lot of different tools to use. It's kind of free form. It's changing shape all the time. Um, I, I don't know if that's a good metaphor, but you're talking about the same idea, right? We're making compounds, but we're doing it in 2 fundamentally different ways. So the nature of how the atoms are holding on to each other is different. And so that is what's causing them to have totally different categories totally different rules for how we name them and how we write their formulas, but they're going to look pretty similar on paper. And so I have to try and help you figure out the details of what it is that's different about them. So let's dig in. I'm going to say these are simple ionic compounds. So let's talk about what makes them simple one more time. Simple ionic compounds contain what I would define as simple metals. Okay, they're not really simple. That's just a term I'm using to help make this easier. What they are actually is main group metals. Okay, main group metals. So here's some examples. And these guys in the beginning too, we're going to do compounds that are only binary and only contain metals with really predictable charges. Okay, so the examples of this are like salt, sodium chloride, Na2O, which is sodium oxide, magnesium oxide, magnesium chloride. And you're going to see right away that we did something different than what we did when we were doing molecular naming. Okay, in molecular naming, if you have two of something, you have to use a Greek prefix to tell me that. So you're going to be tempted right from the beginning to put a Greek prefix in here. But in a weird way, naming binary ionic compounds, compounds that contain metals and only two elements, a metal and a nonmetal, is actually almost easier than molecular naming because you don't need to do any Greek prefixes. Okay, so all you're going to do is just tell me the two names. The only thing that's going to be the same as molecular naming is that you're still going to put an IDE ending on the second name. The first name, the metal, is going to keep its regular name. The metal does always come first and then the nonmetal. Okay, as we get further into this, you're going to see that it's the person who gets a positive electrical charge who goes first, and the person who gets a negative charge goes second. Okay, so that's all there is to it. It's really very easy. So we're going to do this table first. You're going to practice, and we're going to talk about one more time the little pitfalls you could fall into. Okay, so let's do the first like two together, and then you're going to do the other four. We're going to pause the video, and then I'm going to go over them with you. Okay, so this is magnesium, and there's two bromine atoms bonded to this magnesium, but because this is ionic naming, I'm not going to tell you that there's two there. Now, for those of you who are usually a little bit ahead of me, you're probably already wondering, how come this time you don't have to tell me that there's two bromine there? When we get to the reverse process, when we get to the part where we have to write the formula from the name, I'm going to explain to you why this is different, and you don't need to tell me with a prefix how many to put. Okay, so this literally is just magnesium. The metal keeps its name. And then bromine, I'm going to do what I did last time. I'm going to take the ending off where that vowel is, and I'm going to change it to IDE. So this is magnesium bromide. No Greek prefix. Don't say dibromide. That's only for molecular compounds. This is an ionic compound. Okay. So for my second one, I'm going to say sodium because the metal keeps its name, and then bromide. You know what? Let's do three just because I already know that putting the ending on this one's going to be a little tricky for you. Then after this, we'll pause the video. All right, so this is magnesium. All right, so for those of you who are annoyed at me for making you learn so many of your elements, do you see why you have to know them? If you don't know your elements well, and you have to look up every single one of these before you name it, this is going to take you a lot longer. All right, so my second element here is iodine. Sorry about that. I keep hitting something, my control button probably. Okay, this is iodine. Okay, and so same thing we did before. Where the I is, we're going to go right up to there, and we're going to change it to an IDE ending. And so how that's pronounced is iodide, magnesium iodide. Okay, all right, so somebody pause the video. You're going to pause the video. We're going to come back and do the other three. You guys practice, see what kinds of stuff you have trouble with. It could be where you're going to put the ending. It could be that you slip up and try to use a Greek prefix. Don't do that. These are ionic compounds. All right, pause the video. Okay, let's come back. Our last three. This would just be calcium chloride. This one is beryllium. Yes, you have to know how to spell it. Fluoride. And this one is sodium. Now, this one definitely might have thrown you off. Is phosphorus. Okay, I'm going to go to where the O is. That's where I'm going to take it off. And I'm going to put IDE there. It becomes sodium phosphide. Sodium phosphide. Okay, so if you have tricky time trying to figure out where that ending goes, you can also just memorize that it becomes phosphorus becomes phosphide. Okay, so give yourself a minute to fix things that you weren't sure about. And I'm going to head down to the next section. I'll clear that later. All right. Now you're following along with me. You need your periodic table. Okay. One of the reasons you need your periodic table when you're naming is you have to be able to tell where the metals and the nonmetals are for you to decide whether a compound is molecular or ionic and how you're going to name it. What rules are you going to use? Are you using Greek prefixes because it's molecular, or are you not using Greek prefixes because it's ionic? The next thing you have to be able to do now is the reverse process. So, like yesterday, we did molecular compounds. We looked at the molecular formula and then we wrote the name. And then we also looked at the name and we wrote the formula. Okay, so just as a refresher, what is a chemical formula? That's this right here. These are formulas, these are names. Okay, so when somebody asks you for a chemical formula, they're not talking about a math problem. They're talking about the abbreviated version of this name where I just write the symbols of the elements and I give you the actual recipe by using subscripts to tell you how many of each type of atom is in there. Now we have to go backwards. So now we're going to go from the name to the formula. This now brings up the part where you were confused. How come you don't have to say di, tri, tetra? How am I supposed to know how many baryons and how many nitrogens to do? Oh dear, and I started this example off right out the gate with a really difficult. Oh, this was not the best choice of examples. Sorry, you guys, I was kind of in a rush. All right, well, I'm going to be here to go through the first ones with you, so you'll be fine. Okay, so we're going to start here by letting you know that elements pick up what are known as charges. Some elements are not actually going to pick up charges, but we assign charges to them anyway. This is a very confusing concept. So for right now, we're not going to explain why they pick up charges. We're not going to explain why some of them we use the charges and why some of them we don't. I just want you to go through the motions right now of learning how to name, learning how to read names and write formulas, and just trust the process. Next quarter, when we go deep, deep, deep into how atoms work, I'm going to explain this in a lot of detail. Okay. But for right now, I'm going to basically say to you, there are elements on here who have assigned charges, and some of them have multiple charges. Okay. Atoms have the ability to create their own electrical charge. That's how one of the ways that they can stick to each other when they make a bond. When they're doing molecular bonding, they're doing something different than when they are doing ionic bonding. Ionic bonding is a lot more like magnetism, where you have opposite magnets get attracted to each other, opposite charges get attracted to each other. Now, in truth, in real life, I would not recommend opposites attract as dating advice. It turns out it doesn't work. It works really badly in many, many cases. However, if you're an electrical charge, if you're an atom, it works pretty well. So each of the groups on the periodic table, especially for what we know as the main group elements. Okay, so this is something we're going to go over in a lot of detail at different times, but the main group elements are over here. So these guys are considered main group elements. So you may notice on your version of the periodic table, your numbering is different. you have some weird numbering going on where these are called the A elements and these are called the B elements. And the reason for that is because the A elements are considered what we call main group elements, and the B elements are not. Okay, so all that that means, these are the A elements, these are my main group elements. All that that means is that the elements who are included in the main group elements, that's groups 1 and 2, and group 13 through 14 through 18, these guys are following a bunch of patterns that makes them very easy to work with. Whereas the B elements, the people who are not in the main group, the transition metals, and a couple of the people underneath the staircase, they are not going to follow the rules the same way as everybody else does. They will some of the time, but they won't always. And this is one of the reasons why I won't let you have this periodic table yet, because you're going to notice, let me see if I can zoom this a little bit more. You're going to notice when you look at the Regents version of the periodic table that they've got a whole lot of charges written here. Okay, so hopefully you could see it. You guys see nitrogen? You have to use these charges in order to figure out how to write these formulas. So as beginners, the reason why I take this periodic table away from you is because who on earth wants to look at that and try and figure out what to do with it, right? Nitrogen has 8 charges listed there. How are you supposed to know which one to use? So I was pretty shocked by this when I started teaching chemistry at the high school level, because in college we don't get this table with all the charges on it. They just teach you a very simple trick for learning oxidation states, or charges that you put on atoms to use to write ionic formulas. And that trick is so simple that it works way better than giving you the charges on the periodic table. Having all these extra charges usually just confuses people, and then they're not sure what to do or when to use which charges, because that's kind of an advanced skill. And so we don't want you confused. We're not trying to make your life more difficult here. So I'm going to go ahead and put the charges that you're going to memorize, and that's going to make your life way simpler. Okay. Everybody in group 1, this is group 1, right? You're going to label the top of your periodic table or the one on your sheet. They get a +1 charge. Always. They always get a +1 charge. People in group 2, they always get a +2 charge. Always. They always get a +2 charge. Okay. People in the middle, the B people, we're going to ignore them. Those transition metals, they do weird things. See how they all have extra charges? We're going to have special rules for them. We're going to learn them separately. Now, people over here, they do weird things. And we are going to learn that there are some exceptions to these rules. But for you as a beginner, we're just going to follow some general guidelines. And the pattern is very simple. See how we just skipped over these people because they refused to follow the pattern? The pattern keeps going. So if this was +1 and this was +2, guess what this is? It's +3. This is +4. And then a funny thing happens. We're going to slam on the brakes at group 15, and we're going to reverse. We're going to go to a negative charge, and we're going to count backwards. Okay? So people in group 15 are going to have a -3 charge. People in group 16 are going to have a -2 charge. People in group 17 are going to have a -1 charge. And people who are noble gases, they don't like making bonds with people, so this is not going to apply to them at all. Even on this chemistry table, you can see on your paper, they have 0 listed as their charge. They don't participate in any of this because they just don't do bonding, and so they're not going to have charges. Okay, so once you get these charges written down, +1, +2, +3, +4, -3, -2, -1, you're going to assume that in most cases, those are the charges these guys are going to pick up. Do you see how much easier that is than trying to look at this periodic table and figure out which one of those 8 charges you're supposed to be using? That can lead you down a lot of bad roads, trust me on this. All right, so we're going to use these charges to do something called balancing the charges. Okay. In order to, we're going to have to skip around a little bit here. All right. I'm going to actually need to fix this because I included some people who I shouldn't have included in this list. All right. We are going to come back and do barium nitrite. We are not going to do indium fluoride. And the reason why is because indium's a transition metal and he belongs in that other weird group. And I don't want to deal with him right now. Okay. We're just going to deal with the people who have nice, simple charges. Okay, so if you look at your table where you just wrote down, here's the first step I want you to do. I want you to write down the charge we associated with them. So calcium is in group 2, so he has a +2 charge. Now, so you could see why it's so important that you know your elements well enough to rapidly find calcium, know he's in group 2, and know that he should have a +2 charge to do this, okay? Now head over to group 16 where oxygen lives. You're going to see that we have assigned to oxygen a -2 charge. Now we're going to play kind of a little game. Okay, your goal in this game is to get people to add up to 0. Okay, that's how the game works. The rules of the game is you have to get people to add up to 0. You could see here that a +2 and a -2 adds up to 0. Okay, that's how you decide how many of these pieces you're going to put together. So if I only needed one of each of these and I was able to reach 0 that way, then the formula for this compound is calcium oxide. Okay, that's Ca and O. You have one of each of them. And I can already hear how annoyed you guys are. This is not easy. It's complicated. And that's why I'm trying to keep you within strict guidelines. I'm actually trying to reduce your confusion. I'm not trying to make it worse. All right, let's do another one. Take a deep breath. Everybody go find sodium. Sodium is a group 1 metal, number 11 if you go by their atomic numbers. Oh, except for that my stylus won't let me write. Ah, that's what. Thank you. Okay. Sodium. Everybody found sodium? Sodium's a group 1, so everybody group 1 gets a +1 charge. That's easy. Okay, and now nitrogen. I'm going to go over to group 15. Everybody in group 15 gets a -3 charge. Now, again, my rules here, I'm playing, this is like playing a game. The way the game goes is I have to get these two numbers to total up to 0. The rules of the game is that the only way you're allowed to do that is by bringing in a player who has the charge. So let's see if I can make this sound like it makes sense as a game, right? So if you need this player's jersey number, right? You can't have one player with that jersey number playing 3 positions in the game, right? So you're going to need 3 players with that jersey number to balance this out. So I'm going to say that I have extra sodium. And one of the things that throws people off about this process is they're like, where did you get the extra sodium from? How come you're allowed to just pull extra sodium out of thin air? And the real answer to that question is because atoms are very tiny. It's very rare that you would find that you would only have one of them in a container and only one of the other atom. You're dealing with a situation where you actually have millions of these guys and they're all just lining up and waiting to come together because opposite charges attract. So everybody who has a -3 charge, they are able to attract to themselves 3 people with a +1 charge each. Or in the case of this calcium, if I have a +2 charge, I could attract one person who has a -2 charge, or I could attract 2 people who each have a -1 charge, right? So this is, you have to imagine them in kind of a crowded room pairing off with each other based off of their charges. We should invent like a game or something to do in class to make this work. I don't really have time right now, you guys, to invent a game to do this, so you guys are going to have to invent a game to do this. All right, but basically what happens is after I do this, right? This is I follow the rules of the game. Takes me 3 of these guys to balance out that charge. I now have a +3 and a -3, and that's getting me to 0. So I win the game. The next thing I'm going to do when I go to write the formula is I'm going to write down how many did I have to put into the game to win. Okay, so I had to put 3 sodiums. And then I still have 1 nitrogen because he was the one who had the bigger charge. So he was the one I had to balance out. Okay, so this is how you write ionic formulas from names, and this is why there's no Greek prefixes on them. Because as you get better at this, you memorize your charges, you know your elements better, you can do it very, very quickly, actually. I know you don't believe me right now, but you will be able to do it very quickly. Okay, so I'm going to clear this for a sec. I'm going to tell you which ones to do because I want you to do the easiest ones. And then I'll come back and I'll go over the easy ones with you. And then I'll do the more complicated ones. So if we run out of time, you guys, because I think I've already gone on for a while, this is a little bit more of a tough topic. So we're going to skip indium fluoride. That one's too scary. We're going to skip A. We're going to do magnesium chloride, potassium oxide, magnesium oxide, and potassium sulfide. So do those 4. Hit the pause button right now. Hit the pause button and then come back and I'll go over those with you. And then I'll do some of the tougher ones. Okay, so let's go over these. Now, magnesium has a +2 charge. It's in group 2. Chlorine is in group 17. He has a -1 charge. Okay, I have to win the game by getting these guys to be balanced out. I can only do that if I put another player in the game who has this charge attached to him. Okay, so now I have magnesium and 1, 2, 2 chlorines. That's what it took for me to win the game. So this is how I write my formula. Okay, you'll get the hang of it. It's really not that bad. I do have to clear off the screen though, or I'm going to run out of room. All right, next one. Potassium oxide. I'm just going to try and move this up, sorry. All right, potassium oxide. If I go find potassium, I have to know my elements really well because I have to be able to find potassium, who is K, not P. Okay, he's a group 1 metal, so he has a +1 charge. Oxygen's in group 16. He's got a -2 charge. In order for me to win the game, I'm going to need another player who also has a +1 charge. So I'm going to pull another potassium off the bench, okay, out of the crowd, and I'm going to pair them off. I'm going to be a matchmaker. Then I'm going to go ahead and count. I had 2 potassiums to accomplish this. So this is K2 oxygen. Okay. Next, magnesium has a +2 charge. Oxygen has a -2 charge. You're going to see we already won this game. These guys are already balanced out. So I'm going to go ahead and just write MgO. I only needed 1 of each of them. And last but certainly not least, we're going to do potassium sulfide. Okay, potassium again has a +1 charge because it's a group 1 metal. I go over sulfurs in group 16, so he's got a -2 charge. Okay, in order to win the game, I'm going to need another potassium to balance this charge out. So when I write my formula, I see that I need 2 potassium and 1 sulfur to write this formula. Okay, and this is the reason why they don't have Greek prefixes. They don't have Greek prefixes, first of all, because we need a way to differentiate between molecular compounds and ionic compounds, but also because I don't need the Greek prefix. Molecular compounds, because they bond in a different way, they can have many, many, many more atoms attached to them. So you have to tell me what's going on. You have to give me a Greek prefix that tells me that there's 7 chlorine hanging out with that phosphorus atom, right? Otherwise, there's no way for me to know that. But ionic compounds don't don't play the game that way. They play the game by attracting each other by opposite charges. And so that allows me to predict how many people will bond based off their opposite charges. And so that's why I don't need Greek prefixes. I can memorize the charges. Every chemist from here to Switzerland knows these charges, and they can predict what the formula of an ionic compound will be based off of them. Okay, so welcome to the club. Now you know the same thing as every chemist from here to Switzerland. And you should be able to figure out how to do these formulas. All right, since we don't have a lot of class time, I'm going to go ahead and um, talk to you. I'll talk to you on Friday about the more complicated charge balancing. But let me come in and chat with you on Friday and see how bad how mad you are at me by then, about whether or not you think this is hard or you think it's easy. All right, I'll see you tomorrow.